We started with the Schrödinger wave equation in spherical polar coordinates, which we call the Schrödinger wave equation in 3D. And let me summarize that what we did. We started with the time-independent Schrödinger wave equation, which is minus h bar square over 2m del square psi plus v equals E psi when our potential is only dependent on r and it has no dependence on time. Then we use the separation of variables technique, which is r theta phi. We split this into the radial wave function, which is wave function depending on r, and y is theta and phi. This is a wave function which is depending on theta and phi, and as a result of this separation of variable, we got a radial equation and angular equation, and that angular equation, which was in terms of theta and phi, we further split that one into a wave function that depends on theta and into a wave function that depends on phi only. And when we considered that the azimuthally symmetric wave function, means when wave function is not depending on phi, not depending on changing the value of phi, then we got the solution is in terms of the Legendre polynomials, which we call the Legendre polynomials. And when we considered that wave function will be depending on phi, that is when m will non-zero, then we got the solution in terms of the associated Legendre polynomials. And when we were discussing the phi dependent portion, then our solution was e to the power in pi, and finally the solution we got in terms of the spherical harmonics, means the angular equation final solution was that epsilon and 12 plus 1 L minus m absolute factorial divided by 4 pi L plus m absolute and inside a square root, and then E I m phi and P L m of cos theta. This was the final solution, where epsilon was minus 1 to the power m for m greater than 0, means m positive, and equal to 1 when m is negative. We proved that the constant L was running for positive integer values, while the constant m was running from minus L through 0 to plus L, with 2L plus 1 values for each L value. And we also proved that m absolute will always be less than L, because for m greater than L we were having this thing equal to 0. And with this we did some normalizations for the radial wave function. R mod square r square dr was equal to 1, and for the angular wave function y mod square sine theta d theta d phi is equal to 1. So we will have to normalize the wave functions, the radial wave function and the angular wave function separately. And now we will start with the radial equation. That in the radial equation we were having the constant equal to L and L plus 1, and so we will now start with the radial equation. But when we do the radial equation, we need a potential, and for that potential we will have to take an example, and that example is of hydrogen atom that we are taking. So let me start with the solution to radial equation. Solution to the radial equation. So the radial equation is d over dr r square dr over dr minus 2m r square over h bar squared, and v r minus e with r is the radial wave function is equal to L into L plus 1 r. So this is the radial wave equation, and now we will proceed to simplify this equation with a change of variables, and I select that u as a function of r is defined as r, and r is a function of r. Why I am doing this change of variable? Because I want to generate a term like this, and this term can be generated by selecting another variable u is equal to r. And now from here I can write that r is u over r. Now if I take the first differential dr over dr, then this is equal to, if I take u over r, and these are two functions, so first function 1 over r into the derivative of the second function, and then plus, so derivative of the first function which is 1 over r, then it will come plus u, and derivative of 1 over r is minus 1 over r square, so it will come out to be u over r squared. And if I take the derivative of, if I do multiply r square on both sides, then I will get r square dr over dr here. Here I will get r du over dr, because one r will cancel, and here I will get u because r square will cancel. So let's differentiate this again with respect to r. It will be d over dr r square dr over dr. So I have generated this term here, and this is equal to, I will have to take differential of this, and this will be first function into differential of the second. So it will become du over dr square plus then this function into differential of this, which will become 1. So plus du over dr and then minus du over dr. So if I look at this one, these two are cancelling, and I'm having for d by this thing is equal to r d square u over dr squared. So I will have to now put these values back into the equation, and the equation is that this value, so I will put r d square u over dr square for this value minus 2mr square over h bar minus 2mr square over h bar, and then v minus e, and for r I will write u over r, v minus e and u over r is equal to L into L plus 1, L into L plus 1 u over r. Now I will have to manage this as well. If I divide this whole thing with r square, then even with r, if I divide all this with r, then I will get d square u over dr square, d square u over dr square minus, this means I'm dividing this thing, dividing by r. So here I know one r is cancelled here, so one r remaining and it will cancel with this one. So minus 2m v over h bar, and I will write with this u as well from here. Then the next term is plus minus minus plus, so 2m e u over h bar, and this is equal to L into L plus 1 u over r squared. So now I can write this thing. If I multiply this whole with minus h bar square over 2m. Okay, here note one thing, that we are having h bar squared here. So here we are having h bar square, so it is. And now if I multiply with minus h bar square over 2m in order to get rid of this term, so I will have, this will give me minus h bar square over 2m d square u over dr square, and then minus minus it will become plus, so I will have plus vu, and when this one will come over here, it will become minus, so minus with another minus will become plus, and I will have plus, and minus this is h bar square over 2m. So I will have h bar square over 2m L into L plus 1 and u over r squared. So, and this thing is equal to, when minus will multiply with this, it will become minus EU. So it will come on this side and we can write this as EU. Now let me write or simplify this further. I can write this thing as minus h bar square over 2m d square u over d r square, and plus I write this v plus then h bar square over 2m r squared. So h bar square over 2m and L into L plus 1 over r squared, and I take u is common, then this is equal to EU. And if I look at this equation here, that this is somehow like this in one dimension, because this is only the radial dimension. So this one is like the time-independent Schrödinger wave equation, but the V has been modified here, and let me call this V effective, that it is a modified potential which is equal to this value. So it is the same thing, minus h bar square d square psi by dx square plus v of psi equals e of psi. So this is an effective potential, and this effective potential will we will have to solve this equation, but we want to know the value of v, that what is potential. So this potential I will get from the hydrogen atom. The hydrogen, this potential I will get from the hydrogen atom. And why I am getting the hydrogen atom potential, or why I am studying the hydrogen atom, I will have to briefly discuss this thing first in order to show that what is the importance of studying the hydrogen atom, and then we will go to the mathematics. So before going into the import of the mathematical derivation or the solution of the radial equation, the Schrödinger wave equation for hydrogen atom, we will have to first discuss the importance of the hydrogen atom, that why we are discussing this thing. The very first one, so let me discuss the importance of hydrogen atom. Now we know that hydrogen atom is a very simple atom. It is having one proton, which is a charged particle, and one electron, which is going around it. And if I consider that this is a spherical combination or spherical geometry, and we are having our coordinate system like this, then this is our y-axis, this is our z-axis, and this is the x-axis, x, y, and z. And let's say that this is our electron which is on the surface of this sphere. And here I'm having the proton at the center of this atom, which is the nucleus, and here on the surface of this sphere I am having an electron. Now this electron, if it will go along the z-axis from here to here, then this will make an angle theta, and it is at a distance from the origin or from the center at r. Now this electron will follow a circular path as well along the plane, means its projection on this plane, which is the xy plane. So this angle that it will subtend while going around this sphere, this angle is actually phi. So I can mark this angle, and this is the angle phi. So if it moves like this, then it is the zenith angle like this. And for moving like this, it is the angle phi. So it's a simplest atom. Okay, it is the simplest atom, and we can easily study this one. And the next thing here is the set of quantum numbers, because hydrogen atom has been the most studied atom, so we are having a set of quantum numbers, and those quantum numbers we can apply to the complex atoms as well, and this will help us in understanding the periodic table when we will extend this information to other atoms as well. The other thing is that hydrogen atom is the simplest atom, and then we can do the matching or the comparison of theory and experiment very easily. So this comparison is very easy, and we will, with the help of this, means the atomic structure understanding is easy or possible to study the atomic structure, to get more information about the attitude of this electron, that how it goes around this